This is Physics 1060, Lecture 7. Today we're going to be going over Chapter 8, the giant planets. So beyond the orbit of Mars, the low temperatures of the solar nebula allowed condensing bodies there to capture hydrogen and hydrogen-rich gases. This, together with the vast amount of material in the outer solar system, led to the creation of the four large Jovian planets: Jupiter, Saturn, Uranus, and Neptune. It's composed mainly of gaseous and liquid hydrogen and its compounds, so these planets lack solid surfaces, and they may have cores of molten rock. The moons of the outer planets form families of miniature solar systems, although individually each moon presents a unique combination of size, structure, and appearance. So we'll start with Jupiter. It's the prototype of all the giant planets. It actually has more mass than the rest of the planets in the solar system all put together. Jupiter is more than 10 times Earth's diameter and 300 times the mass. You can see the size comparison over on the side. It has dense, richly colored bands or parallel cloud bands that cloak the whole planet. Jupiter is 5 AU away from the Sun, so it means it takes 12 Earth years to complete its revolution around the Sun. Its atmosphere is mostly hydrogen, helium, methane, ammonia, and water. Now it's really difficult to discuss the surface of the planet, since it's mostly a ball of gas. But we can define the surface as the cloud top, and so then we can say a few things about it. The temperature at the cloud top is very cold, about 200 degrees below zero. And the force of gravity there, if there was something to stand on, would be 2.5 times that of the Earth. So in other words, a 180-pound guy would weigh 450 pounds if he could stand at the surface of Jupiter. Now Jupiter is almost big enough to be a second star. If it had been 75 times bigger, which isn't very much in the scale of the solar system, it would have enough mass to collapse down and start thermonuclear reaction, which we'll talk about more when we get to stars. And we'd have a binary star system, and then anytime Jupiter was above the horizon, we'd have a second sun. Now the clouds on Jupiter appear to be particles of water, ice, and ammonia compounds. The bright colors of clouds probably come from complex organic molecules, or sulfur compounds, or maybe phosphorus. Now Jupiter rotates very fast around its axis. It rotates about once every 10 hours, and that fast rotation speed leads to a very significant equatorial bulge. In other words, it is much wider than it is tall. Remember, it's easy for gravity to collapse things down this way, but when it's spinning around, it's very hard to collapse it this way. Similar to if you're on the merry-go-round again. It's very easy to stand up and down, very hard to pull yourself into the center when it's spinning fast. Now if we look at the interior of Jupiter, its average density is about 1.3 grams per cubic centimeter, and indicates its interior is composed of very light elements. Now the interior becomes increasingly dense with depth, and the gas turns to a liquid hydrogen about 10,000 kilometers down. And deeper still, the liquid hydrogen compresses into liquid metallic hydrogen, similar to mercury. And this is a material scientists only recently have created in very tiny, high-pressure diamond cell chambers. Now, there probably is an iron rocky core a few times bigger than the Earth at the center, but this is one of these areas that we're unsure of. Now Jupiter's core temperature is about 30,000 degree Kelvin. That means it emits more energy than it receives, and it's probably due to heat left over from its creation. And the planet may still be shrinking in size, so it converts gravitational potential energy into heat. Now there's a convection pattern on Jupiter. So deep in the interior there's a lot of heat, so that is carried up to the top of the atmosphere in the gas. That high altitude gas then radiates energy into space, and it cools and sinks. So hot material rises to the top of the atmosphere and spreads towards the pole and the equator. Now, since Jupiter is rotating, there's a Coriolis force, and that turns the rising and sinking gases into powerful jet streams that move about 300 kilometers per hour, and we see them as cloud belts. So as the gas comes up from the center, it's pushed one way. As it sinks down to again, it's pushed the other way. So I get bands of gas going opposite direction all along Jupiter. Now, adjacent belts have different relative speeds, and they create vortices of various colors. The largest, of course, is the Great Red Spot, which has persisted since Galileo's time. He was the first one, of course, to look at Jupiter through a telescope, and he noticed the Great Red Spot. We can measure the velocities of different bands. This band up here moves about 270 miles per hour. This one towards the center moves about 220 miles per hour. Down low in the southern half of Jupiter, it only moves about 90 miles per hour. So all the bands move different speeds and have different energy. Now, the Great Red Spot is essentially a hurricane. It's a storm system that's been churning on Jupiter for at least hundreds of years. Like I said, it was first seen by Galileo in 1610. It's much like the hurricanes formed on Earth, but is many times bigger than the Earth itself. Earth would fit very nicely 3 times inside the Great Red Spot. Now, convection in the deep metallic liquid hydrogen layer, coupled with the rapid rotation, creates a magnetic dynamo just like we have on the Earth, except it's much bigger. The magnetic field is about 20,000 times stronger than the Earth's field. It's the largest planetary magnetic field. And because of that, you get auroral activity and intense radio emissions from the magnetic field. This is a picture taken of Jupiter, and you can see up at the top and the bottom the aurora, similar to what we see on the Earth. The magnetic field also traps charged particles far above the planet in regions similar to the Van Allen belts. And this picture here, you can see these dots here. This is lightning occurring in the clouds of Jupiter. Now, why is Jupiter's atmosphere so different from Earth's? The crucial factor here is escape velocity. So, for a planet to keep an atmosphere, the speed of the gas molecules, which will denote V sub mol, must be less than the escape velocity, which will denote V escape. Now, different molecules have different weight. So, for example, a hydrogen atom has a weight of 1. Hydrogen gas, H2, has a molecular weight of 2. Helium gas, molecular weight of 4. Nitrogen, N2, 28. Oxygen gas, O2, 32. Carbon dioxide is 44, and so on. So every molecule has a different molecular weight. Now, from elementary physics or thermodynamics, we can show that the molecular velocity of an object depends on the temperature and the molecular weight of the gas. In other words, the molecular velocity of a gas is proportional to the square root of its temperature over the molecular weight. So the higher the temperature, the faster the molecules are moving. But at a given temperature, the more weight you have, the less velocity you have. Now, earlier we talked about escape velocity, and we said that the escape velocity of an object is the square root of 2 times Newton's gravitational constant times the mass of the planet divided by the radius of the planet. So Jupiter has a very high mass and a very low temperature. And that means that the molecular velocity is much less than the escape velocity, whatever the molecular weight is. So, therefore, Jupiter has an extensive atmosphere of hydrogen and helium. Compare this with the Moon or with Mercury. They have very high temperatures during their days, but very small masses. So that means for these objects, the escape velocity is larger than the molecular velocity for all the common gases, so they have no objects in their atmosphere. The other terrestrial planets, say Mars, Earth, and Venus, are somewhere in between. And different molecular weight gases behave differently. For the heavy gases like oxygen, nitrogen, and CO2, The molecular velocity is less than the escape velocity of these gases and are retained in the atmosphere. However, low molecular weight gases, such as hydrogen gas or helium gas, have high molecular velocities which actually exceed the escape velocities. Therefore, the terrestrial planets can't hold on to their helium or hydrogen that escapes into space. Any helium balloon that you have at, say, a birthday party or whatever, when that balloon pops and the helium escapes, it moves up to the top of the atmosphere, and then those atoms at the top of the atmosphere have escape velocity, and so they escape out into space. So the next planet we need to talk about is Saturn. It's the second largest planet. It's 10 times Earth's diameter and 95 times its mass. It has an average density of 0.7 grams per centimeter. It's less than that of water. So its low density, like Jupiter, suggests that its composition is mainly hydrogen and hydrogen compounds. Now Saturn looks different from Jupiter, ignoring the rings. The temperature is low enough for ammonia gas to freeze into cloud particles that veil the atmosphere of the deeper layers. So the different color is due to all the ammonia gas frozen as clouds at the top of the cloud layer. Saturn is 10 astronomical units from the Sun and takes for 30 Earth years to complete its orbit around the Sun. Now, however, its surface gravity is only 7% higher than that of the Earth's. So our 180-pound guy is going to weigh about 190 pounds. The most striking feature is its rings, which we're going to discuss a little bit later. Now, Saturn also radiates more energy than it receives, but unlike Jupiter, this energy probably comes from the conversion of gravitational energy from falling helium droplets as they condense in Saturn's interior. The winds close to the equator of Saturn reach 450 meters per second, or up to 1,000 miles per hour, and it gets slower down at the poles. We have measured a magnetic field from Saturn, and we can see evidence of it in the aurora on Saturn. This is a Hubble Space Telescope picture taken of Saturn, and we can see the aurora on the northern and southern poles. Now in 1997, a joint mission from NASA and the European Space Agency and the Italian Space Agency was launched. The space probe called Cassini arrived at Saturn June 1, 2004, and it orbited Saturn for 4 years. It took a lot of great pictures, a lot of information, and you can go to the Cassini website at nasa.com, just search for Cassini, and you can see all the pictures and data that Cassini took during its 4-year voyage. That brings us to the next planet, Uranus. It's the first planet that's not visible by the naked eye, and so therefore it needed to be found. It was discovered in 1781 by William Herschel, who was systematically surveying the sky. He was looking at the sky, drawing a very careful diagram of the stars, and looked at another spot, and he came back and he noticed one star had moved. Now, it's small relative to Jupiter and Saturn, but it's 4 times larger in diameter than the Earth, and has 15 times the mass. It's 19 astronomical units from the Sun, so it's really difficult to study from Earth. But even close-up images from Voyager reveal a pretty featureless object. So at 19 AU from the Sun, it has an orbital period of 84 Earth years. It's 15 times more massive than the Earth, but it's only 4 times the size. So the surface gravity is about 0.8 that of Earth. So our 180-pound guy weighs about 140 pounds, and it rotates every 17 hours. Now, Uranus really looks blue, and that's because of the methane molecules in the atmosphere. Methane gas and ice are responsible for that blue color. Essentially, red light is absorbed by methane molecules and blue light is not. And so what gets reflected from the sun is the blue light. Now, its interior has a density of 1.2 grams per cubic centimeter and has a smaller size. So Uranus must contain proportionally fewer lighter elements than Jupiter and Saturn. However, its density is too low to contain much rock or iron. Its interior probably contains water, methane, and ammonia. And the size of the equatorial bulge supports the idea that the interior is mostly water and other hydrogen-rich molecules. It is currently not known if the core formed first and attracted the lighter gases that condensed on it, or the core formed by differentiation after the planet formed. So looking at a cross-section of Uranus, we see it has a layer of molecular hydrogen gas, then mostly water, and maybe a small iron and rock core. Now, one of the strange things about Uranus is it's tilted on its side. Its spin axis is tipped so that it lies almost in its orbital plane. The orbits of Uranus's moons are similarly tilted. We're trying to understand why, and the best hypothesis we have so far is that it was struck during its formation and it splashed out the material that formed the moons. It could be gravitational forces could have tipped it, but we really don't know. We just know it's tipped on its side. So as it's going around at summer or winter, since it's tilted at over 90 degrees, one half of the planet is always light and one half of the planet is always dark until we get to spring and fall where it's half and half, and then in winter we just switch the poles. And finally we get to Neptune. It's similar in size to Uranus. It's a deep blue world with cloud bands and vortex structures. It did have a great dark spot at one time, was its most prominent feature, but that hurricane, that storm, died out a few years ago. It had been established that Uranus's orbit was being distorted by some gravitational pull. And so two mathematicians, John Adams and Urbain Le Verrier, actually predicted where to look at it just by looking at the wobble in Uranus's orbit. And when people then actually looked at where they predicted it to be, sure enough, they found Neptune. Neptune is 30 astronomical units from the Sun, so it takes 165 Earth years for it to orbit the Sun one time. It's 17 times more massive than the Earth, and is about the same diameter as Uranus, so about 4 times that of the Earth. It rotates every 16 hours. Neptune's interior is probably similar to Uranus's, mostly ordinary water surrounded by a thin atmosphere rich in hydrogen and its compounds, and probably has a rock-iron core. Its blue, like Uranus, comes from methane in its atmosphere. But unlike Uranus, Neptune has cloud belts. So it's like Saturn and Jupiter. It radiates more energy than it gains from the Sun. So the deep interior heat drives convective currents, which then lead, via the Coriolis effect, to visible atmospheric bands. Now, all the Jovian planets have rings around them. Of course, Saturn's are the most prominent and were noticed by Galileo, although he didn't know they were rings. Saturn's rings are 300,000 kilometers in diameter, but only about 1 kilometer thick. We can distinguish a few rings from Earth, but close-up pictures reveal hundreds of independent rings. So why do we get rings? Well, there's something called the Roche limit. Any object held together solely by gravity will break apart by tidal forces if it gets too close to the planet. Essentially, we know that gravity depends on the distance between two objects. So when you're close to a planet, something large, the gravity on the part that's closer to the planet is more than that that's further away from the planet, and will literally pull it apart. And we call those tidal forces. Now, the distance of breakup is called the Roche limit, and it's 2.44 planetary radii if the object and planet have the same density. So all planetary rings lie near the planet's Roche limit. Now, the existence of side-by-side ringlets of different compositions indicate the rings are supplied by varied comets and asteroids. Objects bonded together chemically will survive the Roche limit. So, for example, a person in orbit, like an astronaut, is not going to break apart due to tidal forces. It's only things that are just held together by gravity that will be pulled apart. So, if I have some object and I look, I find the Roche limit. Outside the Roche limit, the gravitational attraction is going to distort it. In fact, we're going to talk about Jupiter's moons, Io, the closest one, as being distorted so much as it rotates, it heats up due to the tidal forces. But if you're inside, it literally will break it up into small chunks. So Jupiter does have a ring. We can see it in this picture by blocking out all the light from Jupiter, and you see it has a thin ring of tiny particles of rock dust. It's held in orbit by its gravity. Now, solar radiation and collisions with charged particles trapped in Jupiter's magnetic field exert a friction on that ring dust that will eventually cause the dust to drift into the atmosphere and therefore fall into the planet. So in order to maintain the ring, new dust must be provided, possibly from collision fragments ejected from Jovian moons. Here we have the rings of Saturn. Remember, they're wide but thin. So the main band extends from about 30,000 kilometers above the atmosphere to about twice Saturn's radius. And faint rings can be seen closer to Saturn as well as further away. The thickness of the rings is only a few hundred meters. So look at this picture taken by a spacecraft in orbit of Jupiter. You can see the shadow of the rings on the planet, but we're actually looking directly on at the ring, and look how thin it is, and you can see the moons of Jupiter in the same orbital plane. Sorry, the moons of Saturn. Extremely thin, but extremely wide. Now the rings are not solid, but are made of swarms of individual bodies, and those sizes range from maybe centimeters around to meters around. And the composition of the rings is mostly water, ice, and carbon compounds. It's not uniform across the rings. Notice in here we see rings that have slightly different colors. That means different color means different compounds make up each of those rings. And if we look very close up on it, you can see that they're individual rings, not a large solid band. So how do rings retain their structure? We have large gaps due to resonances with Jupiter's moon or Saturn's moons that are located beyond the rings. Narrow gaps are due to interaction between ring particles and tiny moons in the rings, and we call them shepherding satellites. So for example, I have two larger rocks or something that was captured that are in orbit around Jupiter. We call it a shepherding satellite. So this ring, if things fall too far in, when this shepherding satellite comes by, the gravity pulls it back. Whereas if it goes too far out, the next shepherding satellite will pull it back in and will cause that ring to form a nice, clean band. Uranus also has rings composed of maybe meter-sized objects. The objects are very dark, implying that they're rich in carbon particles or organic materials. The extremely narrow rings may be held in place by shepherding satellites. We would like to send another space probe to Uranus to discover more about its rings. And of course, Jupiter, like the other gas giants, has rings. They're probably debris from satellites and comets that have broken up. They contain more dust than the Saturn and Uranus rings, and they're not even distributed uniformly, indicating that they're relatively new. For example, look at this ring right here. It's very thick on this side and very thin on this side. So it's spreading out, and over many, many, many years will eventually become uniform. And that is all for today's lecture.